Right. Um, so this section is about learning what a limit is and learning limit notation. This is limit notation. The way you read this sentence, this mathematical sentence, is you read it as the limit as x gets close to a number. And so this a would be some number of the function f of x is the y coordinate L. So the answer to limit problems are going to be y coordinates. And there, I really want to emphasize that as x gets close to the number. It's not as if x is equal to a, because we already have a notation for that. That's just f of a. This is if x is close to a, not at a. Okay, we're going to do some examples of this limit notation, and this is an introduction, and we'll do a couple of examples. So one way of thinking about limits is graphically. So here's a graph of a function, f of x. And what if I ask you the limit as x gets close to -2? Well, here's -2. And as my x coordinates get close to -2 in both directions, my y coordinates are getting close to 2. So we say the limit as x approaches -2 of f of x is 2. Now what if I ask you the limit as x goes to 0? Well, here's 0. As x goes to 0 from the right, the y coordinates are getting close to 0. But if x gets close to 0 from the left, the y coordinates are getting close to -2. And since those two numbers don't match, we don't have an answer to this question. We have to say does not exist. There's no way to answer this question because we are close to 0 in one direction doesn't match close to 0 in the other direction. Finally, I can ask you the limit as x approaches 4. So here's x equals 4. If x is equal to 4, our function would be 1. So f of 4 is 1, because that's where the value of the function is. But if x is close to 4 in either direction, our y coordinate here is getting close to 2. And that's the deal with limits. We don't care what's happening at 4. We care about what's happening close to 4. It's different from evaluating a function at 4. All right, here's another example. This is the one we have our function defined as an equation. So here's a piecewise function, or just a reminder about how piecewise function works. If our x-coordinates are less than 0, then we would use this piece, the top piece of the piecewise function, which is a straight line with a y-intercept of 2 and a slope of -1. If our x-coordinates are bigger than 0, then we'd use the other piece of the definition, which is just a straight line with a y-intercept of 0 and a slope of +1. So then here's a question, the limit as x gets close to -2. Well, I would use this part of the definition because close to -2 is certainly less than 0. So the point on that line, if x is close to -2, would be negative -2 plus 2. So it would be 4. +2 plus 2 is 4. There's no problem with just plugging in our number there, but we have to know which piece we would be using of the piecewise function. Okay, here's the limit as x approaches 0. Well, if my numbers are a little bit smaller than 0, I would use the top piece of the piecewise function. And so a little bit smaller than 0 would be basically 0 plus 2, which would be 2. But if my numbers are a little bit bigger than 0, I would use the bottom piece of the definition. And if I'm really close to 0, then my y-coordinate would also be really close to 0. These two don't match. So this limit does not exist because the two pieces are not matching at 0. And this last one, and I want to remind you again that we know that f of 0 is 0 because I would use the bottom piece of the definition for that. But that's a different question than what's the limit as x gets close to 0. All right, now the last question here is asking the limit as x gets close to 4. Well, 4 is bigger than 0, so I would use this piece of the definition, and so that limit would be 4. All right, here's an analytical question with a different sort of piecewise function. This is x minus 2 divided by x minus 2, as long as x is not 2, because if it is 2, I'd be dividing by 0, and that's definitely against the math rules. But if x is 2, then we're going to define our function as 5. So if I ask you the limit as x goes to 0, 0 is definitely not 2, so we would use the top half of our definition. And so close to 0 would be close to -2 divided by close to -2, which would be 1. So as long as if we're really close to 0, our y-coordinate is going to be really close to 1. And then this question is asking the limit as x gets close to 2. Well, close to 2 is not equal to 2. So we're still going to use the top piece of our definition. And now I'm going to do a little bit of example. So imagine that I'm a little bit bigger than 2, like 2.1. So 2.1, f of 2.1 would be 0.1 divided by 0.1, which would be 1. Or I could imagine that I'm a little bit smaller than 2, like 1.9. Then that would be -0.1 divided by -0.1, which is 1. So no matter which way I'm coming at it, this limit would also be 1. And just to emphasize, I didn't ask you for this, but if I had asked you for f of 2, you'd say, well, f of 2 is 5, because that's how this function is defined when x is equal to 2. Limits don't care about equal. Their limits are all about close. All right, the final example, we're going to grab a calculator. I would recommend that you get used to using your calculator, but I'm going to grab Google's calculator because I don't have your calculator on the screen. So we're going to grab that calculator, make sure you're in radians, and we're going to look at, scroll through here. I'm looking at the limit as x goes to 0 of this function, which is sine x divided by x. First of all, convince yourself that just plugging in 0 is not going to answer your question for you, because you'd have 0 divided by 0, which would break math. So we definitely can't just plug in 0 and get an answer. So what we're going to do is grab our calculator, and we're going to do some experimenting. So I'll grab a scientific calculator here. Make sure you're in radians. This out so you don't know what I've been doing. So if I do sine of 0.1 divided by 0.1, that's pretty close to 0. I get 0.998. Oh, that's pretty close to 1. So if I get even closer to 0, like 0.0001, then I'm very close to 1, right? That's true as long as my numbers are bigger than 0, but I should definitely check if my numbers are less than 0, so let's try that. And again, I'm really, really close to 1. And this is how you can use a machine to help you with limits. We're just plugging in numbers that are close to what we are interested in to get that result. So based on what the machine told us, then this limit would be 1, because if we're close to 0, we're getting a value on the calculator that's really close to 1. So that actually turns out to be a really important limit that we're going to come back to, but that limit is kind of a well-known one. I'm actually going to show you one more thing. I'm going to graph that function. If you can graph it on your calculator, great. I'm going to grab Desmos and take a look at that graph. Oh, look, it's already there. So here's that function, and we can see oh yeah, it is getting close to 1. As we're getting close to 0, our function is getting close to 1. If I try doing f of 0, definitely undefined, but if I try doing f of 0.001, I start getting numbers that are close to 1. So I wanted you to see that graph as another way of evaluating that limit, or using technology to evaluate that limit. All right. Thank you so much, and that is an introduction to limit notation.